Hello everyone, how are you? I hope you are all doing well. So in today's lecture, we are going to study Faraday's law of electromagnetic induction. Okay, so basically this is about the induced EMF in case of when we change the magnetic flux with respect to time. Okay, in Faraday's experiments also it was observed that when the magnetic flux was changing with respect to the time, there was one induced voltage. Okay, and that voltage was and it was named as like the induced EMF. Okay, or we can say the induced electromagnetic induction. And on like the in those experiments it was observed that it doesn't matter that in those experiments there were like two coils, and like the one coil is moving with respect to the another one, or the another coil is moving with respect to the first one coil. So the thing is, EMF will be produced when there is a change in magnetic flux. So that is the main cause of, we can say, the induction of EMF. Okay, so now the statement of the after the experiments and all, he thought that there must be one relation between the induced EMF and the change, the rate of change of magnetic flux. Okay, so he stated one statement that the magnitude of magnitude of the induced EMF in a circuit induced EMF in a circuit is, one second, induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. This was given, and its mathematical expression is denoted as mathematical form is given as E equals to minus d phi b upon dt. This is the equation. Okay, and here what is phi b? Phi b is the, here phi b is b vector dot e vector, or we can say magnetic flux. And E is the EMF, induced EMF. Okay, so we can from here also we can analyze that the induced EMF is we can say, if we not talk about the magnitude, then we can say the induced EMF is the negative uh, time rate of change of magnetic flux through a circuit. Okay, and this we can say this Faraday's law of electromagnetic induction is basically made for the closed circuits, or we can say closed loops only, because we know that the current is like current is able to flow in a closed circuit only. So that's why the Faraday's law is mostly used in the closed circuits. Now, here the negative sign, okay, negative sign is just because of the Lenz law that we are going to see. Okay, Lenz law says that the induced EMF, the sign of the induced EMF is such that it will oppose the cause due to it is created. Like it should be the sign should be such that it is opposing its cause of production. Now, for example, like if we are assuming that we are dealing with uh, a system of, or we can say a coil of n turns, and they are closely bound, then the EMF will be, let me write, for n closely wound turns of same flux change, same flux change. Like if there is a same flux change through the each turn, then we can write that EMF will be written as E equals to, in that case, it will be N d phi b upon dt. So this will be the equation of induced EMF. Okay, so basically, if someone asks that how we can increase or decrease the induced EMF, then we know that the magnetic flux depends on the magnetic field and area of the coil. Fine. So we can and we can say, first of all, if we change the flux, then definitely the induced EMF will also going to change according to that. And one another thing is here, if we have unclosely wound turns, then if we increase the number of turns, the induced EMF will also be increased. Fine. So there are many ways to increase or decrease the induced EMF. According to the given questions, or we can say given problems, we will be able to uh, we will be able to predict that the induced will be increased or decreased, because sometimes the in the questions they have given like someone can vary the magnetic field, like they can change the magnetic field, or sometime what they do, they change the shape of the whatever magnetic object is there. So that's why then also the magnetic field, sorry, the area of the magnetic objects will also going to change. Like for example, if a circular wire is shrinked into a straight wire, then their cross-sectional area will be like if its shape is changed, then definitely its properties will also going to change, and they will and the magnetic flux will be also going to change. So there are many ways. Now let's solve the numerical based on the uh, Faraday's law of electromagnetic induction. So one question is given here. Let me see. Okay. So the question is, a square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in the east-west plane. A uniform magnetic field of 0.10 Tesla is set up across the plane in the northeast direction. Okay, the magnetic field is decreased to 0 in 0.70 second at a steady rate. Determine the magnitudes of induced EMF and current during this time interval. So first of all, what they have given, let me write. They have given us that square loop of side 10 centimeter. Okay, if the side is 10 centimeter, for example, the side is given by L, so it is 10 centimeter, and it will be 10 into 10 raised to the power minus 2 meter, or we can say simply 10 raised to the power minus 1 meter. And then what will be the area of the square loop? It will be L square, or we can say 10 raised to the power minus 2 meter square. So this will be the area of the square loop. And what is the resistance here? So resistance is R equals to, sorry, 0.5 ohm it is given. 0.5 ohm. Okay. and it is placed vertically in the east-west direction. Okay, if we see plane wise, then how we can say that? One second. So this will be the coordinate system. Then the equations, sorry, the axis can be seen as this will be the north, and it will be south, and then east and west. So basically, what they are saying that it is placed in a east-west plane. East-west plane means uh, east-west plane means we can say the horizontal plane. And now a uniform magnetic field of 0.10 Tesla. So magnetic field is given as B equals to 0.10 Tesla is set up across the plane in the northeast direction. Okay, so they have set up the, we can say they have set up the plane in the northeast direction. Northeast direction means like this. The plane is set up like that. Now, the magnetic field is decreased to 0 in 0.70 second at a steady rate. And now we have to determine the magnitudes of the induced EMF. Okay, so let me draw here. The magnetic field is basically it will be, if we draw the magnetic field, so they will be like that. Okay, so we know that the northeast plane, okay, so the northeast direction and the east west direction, the angle between or we can say if the plane is placed, for example, if the plane is placed, that square loop is placed in east west plane, then its area vector will be, if it will be in the east west plane, then its area will be in the upward direction. Okay, and the area vector and we can say the magnetic field both are having the angle theta equals to 45 degree. That's why the initial flux here, the initial flux will be initial magnetic flux is phi b, initial is b vector dot a vector equals to ba cos theta. Okay, now we will place the values, then we will get the value of b is 0.10 and the value of a is 10 to the power minus 2 into cos 45 degree. Now its value will be 0.10 into 10 to the power minus 2 into 1 by square root 2. So the value of and its unit will be Weber. Okay, the unit of magnetic flux is Weber. So phi b initial is, we can say 10 raised to the power minus 3 upon square root 2 Weber. Now they have given that the magnetic field is decreased to 0 in 0.70 at a steady rate. So here the final magnetic flux will be, the final magnetic flux that will be phi b into phi b final equals to ba cos theta for the final case. But here the field is decreased to 0. So it will be 0 into a cos theta and final magnetic flux will be 0 Weber. And here the total time taken is 0.70 seconds. So here the value of delta t is 0.70 seconds. Now we know that the magnetic, we can say the magnitude of the induced EMF will be the magnitude of induced EMF is E equals to minus del phi b upon delta t. This will be the equation. Or finally, we can say that E equals to, if we multiply this minus sign inside the, we can say the magnetic flux change, then we will get phi b initial minus phi b final, and its magnitude, because the time is given in the positive, so no need to take its magnitude. So it will be E equals to del phi I minus del phi B upon F into delta, sorry, divided by delta T. So EMF will be basically, what was the equation here? So first equation was 10 raised to the power minus 3 upon square root 2. So it is 10 raised to the power 3 upon square root 2 minus 0. And the time given is 0.70 volts. Now, if we solve it further, then we will get 10 raised to the power minus 3 upon square root 2 into 0.70 volts. So finally, the equation will be 1.01 into 10 raised to the power minus 3 volts. Or if you want to convert into the millivolt, then the equation will become as, one second. Okay, so in millivolt also we can convert it. E equals to 1.01 millivolts. So this will be the magnitude of induced EMF. Now in the secondary thing, they are asking us to find out the current during this interval. So what will be the current? Current will be the induced current is I equals to EMF upon resistance. So it will be, what is the value of EMF here? 1.01 millivolt, and the resistance is 0.5 ohm. So it will be basically 1.01 divided by 0.5 milliampere. So current will be 2.02 ampere. So this will be the equation of current here. Okay, so that's how we can solve the problems based on the Faraday's law of electromagnetic induction. Now let's solve the another question in which the number of turns is also included. So the question is given as a circular coil of radius 10 centimeter, 500 turns and resistance 2 ohm is placed with its plane perpendicular to horizontal component of the Earth's magnetic field. It's rotated about its vertical diameter through 180 degree in 0.25 seconds. Estimate the magnitude of EMF and current induced in the coil and the horizontal component of the Earth's magnetic field is given as 3.0 into 10 to the power minus 5 Tesla. So first of all, what the things are given here? Let me write. Solution. Radius is given. Radius is 10 centimeter, or we can say 10 to the power minus 1 meter. And the number of turns is n equals to 500. The circular coil is given. So, and the resistance is R equals to resistance R equals to 2 ohm is given, and it is placed plane perpendicular to the horizontal component of Earth's magnetic field. And the Earth's magnetic field is given as B equals to 3.0 into 10 raised to the power minus 5 Tesla. And what else things are given? Okay, the time taken is 0.25 seconds. Okay, in the first case, we have to find out the initial magnetic flux through the coil. So what will be the initial magnetic flux through the coil? It will be the initial magnetic flux through the coil. What is the initial magnetic flux through the coil? Phi b I equals to b vector dot a vector, or ba cos theta. And now the task is to find out the value of theta. What is theta here? So according to the question, uh, the circular coil was placed plane perpendicular to the horizontal component of the Earth's magnetic field. So as we know that it is placed perpendicular to the horizontal. Perpendicular means this is the horizontal surface, and the circular coil is placed like that. So obviously we know that the direction of the area vector of the circular coil will be towards this direction. So the horizontal direction of the magnetic field and the area vector are in the same direction. So therefore here theta will be same. So, theta will be like the direction of the magnetic field and the area vector will be same. So therefore the theta will be 0 degree. So we can write, and the here the circular coil is given, so its area vector will be pi r square. So basically the equation will become b into pi r square cos 0 degree. Now let's place the values. So value of b is 3.0 into 10 to the power minus 5 into pi into the value of radius is 10 to the power minus 2, and the radius square will be 10 to the power minus 1 ka square, and cos 0 is 1, and the unit is Weber. So its value will be 3.0, 3.0, or we can say 3 pi. So in the calculating it again and again, it will be very easy for us to like take the calculation at the end. So the we can say calculation error will be less. So 3 pi into 10 raised to the power minus 7 Weber, because here 10 raised to the power minus 1 one's square will be 10 raised to the power minus 2, and 10 raised to the power minus 5 plus 10 into 10 raised to the power minus 2, it will be minus 5 minus 2 is minus 7. So it is the initial flux. Now our task is to find out the final flux. So in case of final flux, it's rotated about its a vertical diameter. Like the circular coil was like that. Now its vertical diameter will be like that. So it is flipped, it is rotated about its, so it will be we can say the orientation will be like that. So now this time the area vector will be in this direction, and the horizontal, we can say the horizontal component of the Earth's magnetic field will be in the opposite direction. So here, so the theta will be, in this case theta will be 180 degree. Therefore the final magnetic flux will be, the final magnetic flux through the coil is phi b final equals to ba cos 180 degree. Okay, here the magnetic field is not changing, nor the area. So therefore the value will be same, but it will be multiplied by cos 180 degree. So value of the cos 180 degree is minus 1. So therefore we will just place the values, minus 5 into pi into 0.1 square into cos 180 is minus 1 and the unit will be Weber. So therefore we will get the minus 3 pi cross minus 7 Weber. So this will be the final flux. Now our task is to find out the magnitude of EMF. So the magnitude of EMF will be the magnitude of EMF is E equals to minus del phi B upon, and the number of turns will also be multiplied, minus n del phi B upon delta T. This will be the equation. And finally, we can say that if the minus sign will be multiplied inside, so it will be n phi B initial minus phi B final. Okay. And it is divided by time delta T. This is the equation. So finally, we will get the value of n is given, that is 500 turns. So basically, we will get 500 multiplied by initial flux. Initial flux is 3 pi cross 10 to the power minus 7 minus the final flux is minus 3 pi cross 10 to the power minus 7. So, and the time is 0.25 seconds and the unit will be volts. Okay. Then if we finally calculate, then we will get E equals to 500 into this minus and minus will be plus, minus into minus will be plus. So finally we will get 6 pi into 10 raised to the power minus 7 and it is divided by 0.25 volts. So after the final calculation, we will get its value is equals to its value, it is 3.8 into 10 raised to the power minus 3 volt. 3.8 into 10 raised to the power minus 3 volts. So this will be the value of induced EMF. Now they are asking us to find out the induced current also. So what will be the induced current here? The induced current in the coil is I equals to EMF divided by resistance R. So it will be I equals to 3.8 into 10 to the power minus 3 divided by its resistance, and the resistance is given as 2 ohm. So basically it will be ampere. I equals to 1.9 into 10 to the power minus 3 ampere, or we can say I equals to 1.9 milliampere. Okay, so that's how we can solve the questions based on Faraday's electromagnetic induction, where either the question is just related to a we can say single coil, or we can say there may be n number of coil. We can say n number of turns in the coil. So we can solve the questions. If you have any doubt, then you can ask in the comment section. We will be try to resolve them in the next video or in the comment section itself.